Okay, Kiara starts at 22 meters along the coordinate axis, so that's her location. She undergoes a displacement of minus 41. That means she moves to the left by 41 meters. What is her final position? And again, if you want to review this concept, hit review here, and this will take you to the section of the book that covers this topic. Let's take a look at this in more detail. Okay, so we're starting at 22 meters. We undergo a displacement of minus 41. That means you move to the left 41. Where do you end up? Okay, so from this chapter, displacement is where you end up, x final, minus where you begin, x initial. Sometimes this is called x2 and this is called x1. Sometimes this is x0, this is x1. Just so you know that this means later. This doesn't mean that you're finally there and you're never ever going to move again. This just means your later coordinate. This means your earlier coordinate. So here's what we were given. You start at 22. Here's the displacement. Here's what we're trying to figure out. Okay, so then we'll have to do a little bit of algebra. This one you could kind of do in your head, but I'm just giving you the whole treatment of it. So I'm trying to figure out x final. So I'll have to add x initial to both sides to give me x final. That's what I'm trying to figure out. So minus 41 meters plus 22 meters is x final. Okay, so it looks like about you take this plus this, whatever you get for that. By the way, you might have different numbers than I have. This is just the first problem. Okay, so it looks like maybe minus 19 meters or so. You'll have to double check my math, but I think this is a good answer for that one. Okay, let's see what else we have. Okay, here's the next problem. This figure shows the motion diagram for a horse galloping in one direction along a straight path. Not every dot is labeled, but the dots are equally spaced in time. Okay, so this is a motion diagram. What is the horse's velocity during the first 10 seconds of its gallop? Okay, so we're assuming we start here at about 600. After 10 seconds, there's a little bit of information when I hover above this dot. Now we go to this dot. This is 10 seconds. So they're asking about the first 10 seconds. So we started at 600. We ended up at 500. And this took 10 seconds. So we can figure out the displacement for that. We'll do that in just a moment. What's the horse's velocity from 30 to 40 seconds? Okay, so here's 30, here's 40, and then from 50 to 70. So at 50, we're at 250. At 70, we're over here at 50. Okay, so let's just do the first one. The other ones are just like the first one. Okay, let's take a look at this. So again, we start at 600 and we end up at 500, so initial, final. This took 10 seconds. The velocity is delta x over delta t. Probably we have a little bit of vector sign here. That just means make sure that you take into account the direction. Sometimes this is just called t when the initial time is 0. I'll just keep calling it delta t, which is 10 seconds in this question. Okay, so the displacement is where you end up, 500, minus where you began, 600. So you can see that that's going to come out to be negative over 10 seconds. So minus 100 divided by 10, or minus 10 meters per second. Now the negative sign means you are moving to the left, and that's exactly what was happening in the motion diagram. Okay, parts B and part C are really similar to that. Just make sure that you have the correct time increment there. Okay, let's look at the next one. Okay, the third one is convert these to SI units. So remember, SI units are meters, kilograms, and seconds. So you'll have to look up the conversion factor in the book. This, I wouldn't give you one like this on the test, like convert 13 inches into meters or anything like that. But this is a good skill to have to do some of these problems. So so take a look and see how many inches are in a meter, or maybe you have to go inch to centimeter, then centimeter to meter. Here's the part of the chapter you can review. Okay, there's a conversion factor from feet to second to meters per second. Same thing with this one, miles per hour backwards over here, or not backwards, but miles per hour to meters per second. So take a look back here in that section. I'm not going to do this one for you, but make sure you can do this, especially when you're going from, say, centimeters to meters, that sort of thing. Next problem. Loveland, Colorado is 18 kilometers due south of Fort Collins and 31 kilometers west of Greeley. What's the distance between Fort Collins and Greeley in kilometers? Okay, so this is a little bit of a trig review. Let's take a look at it. Okay, so we went the Fort Collins to Greeley distance. We want this distance. So we're given this part and this part. This is a right angle, so this is a Pythagorean theorem problem. So review your trig if you're confused about this one, but basically a squared plus b squared is equal to c squared. So 18 kilometers squared, squared plus 31 kilometers squared would be equal to this distance squared. Or if I take the square root of that, that would give me the distance between those two. Okay, so make sure you punch it in your calculator correctly. It shouldn't be too big of a problem. You know, the answer's got to be bigger than 31, so whatever that turns out to be. Okay, let's look at the next one. Okay, so this is another trig review type problem. Black vultures excel at gliding flight. They can move long distances through the air without flapping their wings, while undergoing only a modest dip in height. A vulture is typically in a typical glide in still air moves a path tipped 3.5 degrees below the horizontal. If the vulture moves a horizontal distance of 100, how much height does it lose? Okay, yeah, let's take a look at this. We definitely need a picture for this one. Okay, so here's a picture of this scenario. 100 meters horizontal, 3.5 degrees. How far down did we dip when this happened? Okay, so review sine, cosine, tangent, all of those. So look, here we have this picture. The tangent of 3.5 degrees is the opposite side, h, over the adjacent side, 100 meters. So then h is equal to 100 meters times the tangent of 35 degrees. So make sure your calculator is in degree mode when you do this. So I'll just do it like this on my calculator. 100 times the tangent of 35, and I'm already in degree mode. So something about 70. Whoops, it's 3.5, not 35. Okay. Yeah, this 70 doesn't make sense, right? If you're not falling very far, that didn't make any sense. So I caught myself. 100 times the tangent of 3.5 degrees. So do answers make any sense? This is a good way to catch yourself. All right, that's better. 6.11 is the answer for this one, and it's in meters. Okay, good. So a little trick. If an answer doesn't make any sense, go back and check your work. So let me actually enter this. So I got 6.11. Let me just show you what happens if you put 6.11. Submit. It turns green here. Correct. Your answer was either rounded differently or used a different number of significant figures than required. It won't count you wrong for having the incorrect amount of significant figures. So when you're doing these problems, keep all your numbers until the end and then round off. Okay? And it won't count it wrong. The problem arises if you round things. Say you had to do several steps. You round it off, you round it off, you round it off. By the time you get to the final answer, you've rounded it so much you're outside the tolerance of this mastering physics. So, keep all your digits until the very end and then round off. Okay. Let's look at the next one. Okay, this is a position versus time graph. Whenever you see a graph, make sure you look and see what's being graphed. Position versus time. You're used to x versus y. These motion diagrams are always going to have position versus time, velocity versus time, acceleration versus time. Okay, so let's see what we have here. The position graph shows a dog slowly sneaking up on a squirrel. So we start at 6, and then we go towards the origin. So we go from 6 to 4 in 8 seconds. And then we go from 4 meters down to 0 meters in only 2 seconds. So how many seconds does the dog move at the slower speed? Okay, so I sort of already answered that for you. This is the slower speed. This part, you're not moving as quickly. The slope is less. The slope is greater, magnitude-wise. So I would say 8 seconds, we're going at the slower speed, right? This part's the slower speed. We start at 6, and we end up at 4. That takes 8 seconds. Okay, so think about that one. Next one, Major League Baseball, the pitcher's mound is 60 feet from the batter. If a pitcher throws a 91-mile-per-hour fastball, how much time elapses from when the ball leaves the pitcher's hand until it reaches the batter? Okay, so you know you're going at 90 miles per hour, and we're traveling 60 feet. How long does that take? Okay, so the speed is the distance divided by the time. You have to figure out the time for this one. Just be careful with the units. This is 60 feet. This is 91 miles per hour, and we want the answer in seconds. Okay, so I'll just say the speed is the distance. This is the distance divided by the time. You'll have to figure out the time. And then just be careful with the units, miles per hour and feet here. You'll have to put them in the same units. And again, hit review if you're, want some more background information for that one. These are in Chapter 2 now already. In an 8-kilometer race, one runner runs steady at 11 kilometers per hour. Another runs at 14.7 kilometers per hour. How far from the finish line is the slower runner when the faster runner finishes the race? Okay, let's take a look at this. Whoops. Let's take a look at it. Sorry, I hit the wrong button. Okay, so the race is 8 kilometers. Slower runner 11 kilometers per hour. Faster runner 14.7 kilometers per hour. How far is the slower runner from the finish line at the point where the faster runner finishes? So remember, the speed is the distance divided by the time. So let's figure out how long it takes the faster runner to finish the race. And then once we know the time it takes the faster runner to finish the race, we can see how far the slower runner has run during that time, and then figure out how far that runner is from the finish line. Okay, so we'll have to do a little bit of algebra. So time turns out to be distance divided by speed. So the distance is 8 kilometers. The faster runner is running at 14.7 kilometers per hour. Our answer will be in hours then. Right, the kilometers cancel out. The hours come up to the numerator here. So 8 divided by 14.7. So 0.544 hours. Okay? That's how long it takes the faster runner to run 8 kilometers. Now let's see how far the slower runner has run during that time. Okay, so same formula here. Distance is velocity times time when you do the algebra. Multiply both sides by t. So 11 kilometers per hour times 0.544 hours. That'll tell us how far the runner has traveled. And I haven't changed my calculator, so I'm just going to use that times 11. 5.98 kilometers. Okay, so this runner has gone 5.98 kilometers. The runner needs to go 8 kilometers. Let's see how far from the finish line. So minus 8, 2.01 kilometers. And then you might have different numbers, so just be careful with that. Okay, so several steps, and this is what I was saying. I kept all the numbers. I didn't round this off in my calculator. I left it as 0.544. On my calculator, though, I had more digits. All right, let's look at the next one. Okay, here's the next one. A somewhat idealized graph of the speed of blood in the ascending aorta. So it's a biology question. During one heartbeat appears in the graph. Okay, so the speed goes from 0 up to 0.75, and then back down to 0 in 0.2 seconds. What do we want to know here? Approximate how far in centimeters does the blood move? Okay, so this is a velocity versus time graph. Okay, whenever you see graphs, what's being plotted? That's the first thing to look at. So we've got velocity versus time. So the area under a velocity versus time graph gives you the displacement. So if you can figure out this area, the area of the triangle here, you can figure out the displacement. That's what they're asking here. This is a triangle, so the area of a triangle is 1/2 the base times the height. So we'd have 1/2 the base The base here is 0.2, right? From 0.2 to 0.4. The base here is 0.2. The height is 0.75. That's in meters per second. So figure out the area of this triangle. Make sure that you convert it to centimeters, and then you'll have the displacement. Okay. Assume similar data for the motion of blood in the carotid artery, which connects the aorta to the brain. Estimate how many beats of the heart it will take blood to move 30 centimeters. Okay, so you know how far it will move in one beat from the first answer. How many beats do you need for it to go 30 centimeters? Okay, very good. So you'll have to figure that out. You know how many for one beat. How far do you need it to go for 30 centimeters? Okay, next one. Ooh, okay, so here's a lot more graphing going on. We set the origin of a coordinate system so that the position of a train is located at 0 at t is equal to 0, figure 1. Okay? Figure 1 shows the train's velocity. Okay, so yeah, let's take a look at this. This is the velocity versus time graph. First thing to look at is velocity versus time. Okay, so from down here at 0 seconds, we're at -2 meters per second. And now we're at -1, and then we're at 0 meters per second. 0 meters per second means you stop for an instant. And then over here at 3 seconds, we're going at 1. Here, we're going at 2. So we were going in the negative direction, but slowing down because now we're at -1, and then we stop. So we were moving to the left for 2 seconds, stopped. Now we're moving back towards the right, and the speed is increasing. Once you hit 4 seconds, then we're just stuck at 2 meters per second. Right? This is a constant speed here. So from 4 seconds on, we're going at a constant speed. So from 4 seconds on, the position versus time graph should be just a straight line with a slope of 2, right? Because that's the speed here. So from 4 seconds on, the position versus time graph should have a slope of 2. Okay, so from 0 seconds up to 4 seconds, the velocity is changing. So we'll have to have a graph that corresponds to that. Let's take a look at these and see if we can weed some of them out. Okay, so the first one we could weed out right away because after 4 seconds, we have this kind of a graph. And what I said was it should be like a nice line here because the velocity is constant. So it can't be that one. So here's a nice linear part here. So this is still in the running based on the 4 second and greater time. Same thing with this one, right? Over 4 seconds, we have a nice positive slope here, corresponding to positive 2 meters per second. Also cannot be this one, right? This is a negative slope. Okay, so it's between B and C. This graph says from 0 to 4 seconds, you're not even moving. You're at coordinate 0, and that does not change. This one says, you look at the slope of the tangent line, the velocity here is negative, getting less and less negative. Here's the tangent line at 2 seconds. It's just a horizontal line, so that means the speed is 0. And now the slope of the tangent line gets greater and greater and greater. So it's got to be this choice here. Okay? Choose the correct acceleration graph for the train. Okay, so from 4 seconds on, the acceleration is 0 because the velocity is not changing. Let's see what we can weed out from this one. All right, this one will work. First one doesn't have a 0 velocity after 4 seconds. This one also doesn't have a 0 velocity. Okay, this one does have a 0 velocity. Okay, from 0 to 4 seconds, this is the velocity versus time graph. The slope of this is the acceleration. So the acceleration is positive. Here the velocity is becoming less negative, and then here it's becoming more positive. Those are the same things. So the slope here, it looks like in 2 seconds the velocity changes by 2. I'm looking at from 2 to 4 seconds. The velocity changes by 2. We go from 0 to 2, and it happens in 2 seconds. So the slope here is 1. Same thing down here, the slope is 1. Okay, so let's see which one corresponds to that. Here we go. The acceleration of 1 meter per second squared from 0 to 4 seconds. And then once you hit 4 seconds, there is no acceleration. The velocity is constant. Okay, so these graphs, just take your time, see what's being graphed. You should be able to go from one sort of graph to another graph like we did in this problem. Next problem. Thomson's gazelle could reach a speed of 13 meters per second in 3 seconds. A lion could reach a speed of 9.5 in 1. A trout can reach a speed of 2.8 in 0.12 seconds. Which has the greater acceleration? So just calculate the acceleration for each of these and see which one is greatest. Let me actually use that link here and show you the formula for that. Okay, should be coming up here in a second. Okay. Change in velocity over the change in time. So they give you the change in velocity for each of them. They give you the amount of time, so figure out the acceleration for each of those. Okay, very good. Whoops. So don't be surprised if it's the trout. Okay, so I hit review and then I hit that part of the book. All right, next problem. A light rail passenger train provides transportation within and between cities, speeds up and slows down with a near constant and quite modest acceleration. A train travels through the congested part of town at 6. Once free of the area, speeds up to 11, and this happens in 8 seconds. Okay, so we go from 6 to 11 meters per second in 8 seconds. At the edge of town, the driver again accelerates with the same acceleration for another 16 to reach cruising speed. So what's the final speed? Okay, so we start at 6, go to 11. This happens in 8 seconds. Okay, so you can figure out the acceleration for the first part, for the change in speed part. And then once you hit the edge of town, going 11, then you speed up for another 16 seconds at the same rate. So what speed do you actually reach? All right, let's take a look at this. Okay, we go from 6 to 11. This happens in 8 seconds. And then once you hit the edge of town, you go from 11 to some unknown speed, but you accelerate for 16 seconds at whatever rate you had here. Okay, so let's figure out the acceleration from this part. Delta V over delta T. So 11 meters per second minus 6 meters per second. This happened in 8 seconds. So this would be 5 meters per second divided by 8 seconds. So 5/8 meters per second per second. That's the correct way to say it. Usually we just write it as meters per second squared, but a meters per second squared means meters per second per second. So 5 divided by 8. 0.625 meters per second, but you can write it like this. So you have that acceleration, and then we're going to go from 11 to some final speed at the same rate. They tell you that in the problem. Okay? And then what's the final speed here? Okay, so the acceleration, final minus initial, divided by the amount of time. Here's the amount of time, 16 seconds. So I have to do a little bit of algebra. Multiply both sides by t. So I multiply both sides by t, and then add the initial speed to both sides to get the final speed. Another way of thinking about it is, all right, you started at 11. After one of these seconds, you're at 11.625, and then after 2, you're at 11.625 plus 0.625, etc. That's what this formula tells you. Okay, so put it all together and you can get the final speed. All right, let's look at the next one. Okay, so a speed skater moving across frictionless ice at 9 meters per second hits a 6 meter wide patch of rough ice and then slows down steadily, then continues at 6 meters per second. What is her acceleration on the rough ice? All right, let's take a look at this. Okay, so here's what I have. We start at 9 meters per second. We go through a displacement of 6 meters. We end up at 6 meters per second. What's the acceleration? So take a look back at the kinematics equations we have. We have to figure out which one will work for us here. So remember, we have velocity final is equal to velocity initial plus AT. Velocity final squared is equal to velocity initial squared plus 2a delta x. And then delta x initial velocity times time plus 1/2 at squared. These are our three kinematics equations. So based on what we're given and what we're asked for, we have to sort through these three equations and figure out which one to use here. Sometimes maybe you got to use two of them actually. The one thing to note is the first one that I've written here and the third one involve time. We don't know anything about time. We're given displacement. All of the equations have acceleration in them, though. Okay, so let's take a look. Because we don't know the amount of time, maybe this one will be helpful for us. Let's see if this will actually work. Okay, we know the final speed. I'll put a little check mark. We know the initial speed. Good. We know the displacement. Good. The only thing that we don't know is the acceleration. So we'll have to do some algebra. That's how this physics stuff works. You have like a general equation. You might have to do some algebra based on what you're given and what you're looking for. Now, sometimes there's more than one way of doing a problem. Maybe not so much in this problem, in this question, because we don't know the acceleration. I was thinking maybe we could use the first one to figure out the acceleration or the time, but we can't because we don't know the acceleration. So we're going to have to use the second one here. Okay, so final velocity squared is equal to initial velocity squared plus 2a delta x. And we're trying to figure out a. So we've got to get a by itself. Okay, so final velocity squared minus initial velocity squared is equal to 2a delta x. And then I'll have to divide both sides by 2 delta x to be able to get the acceleration. Okay, so just be careful when you do this, make sure you're dividing the numerator by the denominator. So don't be surprised when this comes out to be negative, which it should because you're slowing down. You're going from 9 to 6. Okay, so put your numbers in. You might have different numbers than me, and you should be able to get it that way. It takes practice to figure out which equation to use. Again, it's based on what you're given and what you're asked for. Okay, let's look at the next one. Okay, so a driver has a reaction time of 0.5 seconds. That means nothing happens in 0.5 seconds. You're driving along at a certain speed. It takes you half a second to even do anything. So in that time, you move a little bit. And a maximum deceleration of 6 meters per second squared. So if you wanted to put that in as a number, that would be negative 6 meters per second squared. It means you're slowing down. She's driving at 20 meters per second when she suddenly sees an obstacle in the road 50 meters in front of her. What is the distance she travels, the distance she passes after noticing the obstacle? Okay, let's take a look at this. Okay, reaction time of a half of a second, speed 20 meters per second, deceleration of 6 meters per second squared, so that's where the minus sign. So how far do we travel during this whole thing? Okay, so the first part, during the reaction time, we travel a distance at a constant speed. So distance divided by time would be speed here. So the distance we travel during this first leg of the trip would just be speed times time. So 20 meters per second times a half a second, 10 meters before anything even happens. Okay, so this is the constant speed part before you even hit the brakes. Now you hit the brakes going 20 meters per second, you slow down at this rate. How far are we going to go during this part? So I'm just going to call this like D1 or something like that. Let's figure out the displacement for the second part, where we go from 20, now stop means this, final speed of 0. We've got to bring that to the problem. It says stop, it doesn't say final speed 0. It means the same thing though. Okay, so let's see if we can go back to these kinematics equations and figure out how far we move during that part. Final speed 0, initial speed 6, deceleration minus 6. We can figure out the displacement during this part of the trip. This is like the total displacement here, right, that we're actually looking for, which includes the 10 plus whatever we get in the second part. Okay, so we can use the second kinematics equation again to figure out how far we travel when we go from 20 to 0 at this rate. Okay, so it's really two problems. The first problem is this part, and then the second problem is figuring out how far you travel under these conditions, and then we'll have to add both of those distances together. Okay, so Same thing that we had before. Final speed is equal to the initial speed to a delta x. The thing that we don't know this time, though, is delta x. Okay, so let me do the algebra here. I wait until the very end to put the numbers in. So let me subtract initial velocity squared from both sides. So I've done that. And then divide by 2a. That'll give me delta x. So I'll leave that part up to you. Remember, final speed is 0 minus the initial speed squared. So minus 400 squared. And then divided by 2 times minus 6. So that's where the minus sign goes away. And then you'll just have some number for delta x here. And then the total distance that you need, so the total distance will be what you got from the first part plus what you got from this part. And then you'll see part B asks you, do you have enough time to stop? Let's look at the next one. So a gannet, next one here, is a seabird that fishes by diving from great heights. Gannet or gannet, I'm not sure how to pronounce it actually, hits the water at 32 meters per second. What height? From what height did it dive? Assume the gannet was motionless before it started the dive. Okay, so it starts at a certain height, just under the influence of gravity, reaches a speed of 32. What was the height that it dove from? Let's take a look at this. So this is free fall. This is just a special case using our kinematics equation, knowing the acceleration in the y direction is negative 9.8. Let's look at this. Again, starting from rest means the initial speed is 0, and we're diving, so we're going in the negative y direction, so the speed here is negative 32 meters per second. The acceleration in the y, this is what you have to bring to the problem. Free fall, negative 9.8. What is delta y? All the kinematics equations we had before still work. We do not know anything about the time, though. So velocity final squared in the y, velocity initial squared in the y, plus 2 acceleration in the y, delta y. This is the kinematics equation we can use. The other two involve time, which we don't know anything about, and they don't ask us about it. Now you could figure out how long it would take to go from 0 to 32 with this rate if you needed to. You could use the first kinematics equation to figure out how much time it takes. Okay, so you can use this one. Initial speed is 0. You'll have to do the algebra again. So if this is 0, divide both sides by 2 acceleration in the y, which that's free fall, negative 9.8. That'll give you the displacement in the y. Okay, on to the next one. Okay, let me just say a few things about this one. Steelhead trout migrate upriver to spawn. Occasionally, they need to leap up small waterfalls to continue their journeys. Fortunately, steelheads are remarkable jumpers, capable of leaving the water with a speed of 8 meters per second. So that would be their initial speed. Now, if your initial speed is 8 meters per second, and your final speed is 0, and the acceleration in the y is negative 9.8 meters per second squared, what's the maximum height you can jump? So similar to the last problem, actually. Not exactly the same because we're going kind of in reverse. It's the same idea, though. Again, you know the initial speed is 8. You know the final speed is 0. That's at your maximum height. You know the acceleration in the y is negative 9.8 meters per second squared. Figure out the displacement. So use the kinematics equation that we just talked about. Okay, and I'll leave part B to you to take a look at. Again, it's using kinematics, and you know all the knowns. All right, let's look at the final one, actually. In an action movie, the villain is rescued from the ocean by grabbing onto a ladder hanging from a helicopter. He is so intent on gripping the ladder that he lets go of his briefcase of counterfeit money when he's 130 meters above the ground. If the briefcase hits the water 6 seconds later, what was the speed at which the helicopter was rising? Well, if the villain is holding onto the suitcase and the villain is also holding onto the helicopter, whatever speed the villain is rising is the same thing that the briefcase was initially rising. So when you drop something in this situation, if you're holding onto a helicopter going up, the briefcase doesn't immediately start going down. It goes up a little bit because dropping means you just let go. It doesn't mean that the initial speed is 0. So the briefcase will actually rise up a little bit and then go down. It's just like if you're riding in your car and somebody drops something out of the car, it doesn't hit the ground there. It has some forward speed. All right, let's take a look at this. Okay, so the helicopter was 130 meters above the ground. The helicopter keeps going. When you let go of the briefcase here, it goes up a little bit, and then it comes back down. Okay, so the distance it traveled is 130 meters, but the displacement is negative 130. The briefcase went up and went back down. Displacement is where you end up. You ended up down here. You started up here. The displacement is negative 130. Acceleration due to gravity, negative 9.8, just under the influence of gravity. This takes 6 seconds. Now we've got two kinematics equations that involve time. I'll just put a little y here to emphasize that. We also have delta y, initial velocity in the y times time, plus 1/2 acceleration in the y times t squared. Now the problem with using the first one to figure out the time is we don't know the speed right before it hits the ground. The final speed's not 0. We need the time the instant before it hits the ground. You can use this one, though, to figure out the initial speed, right? You know the displacement, negative 130. The time is given. You know that. Again, you know the time, you know the acceleration of the y. You'll have to do some algebra for this, but you can use this equation to figure out the initial speed. It should come out to be positive, right? It goes up, comes back down. Lots of other ways of doing this problem. I'm just showing you the cleanest way to just do it in one step. You can figure out maybe how long it takes to get to the highest point, then figure out how long it takes to get from the highest point down. Several different ways of doing it. I'm just doing it in one step. Okay, if you have any questions, send me an email and I'll talk to you soon.